I don't know how to do this anymore. Let's try this. All right. What do you mean it's paused? All right. All right. Hello? All right. Trying to get this to work. How y'all doing? Yeah. So I got thrown a little off trying to get stuff prepared, but it's not too bad. See how it goes. Has anyone looked at the homework? Is everyone okay with it so far? All right, I'll try to have, I need to figure out sapling. I'm having a problem with using it here. Mostly I can't remember my password, so I have to go find it. But certainly if you have questions on the homework at the end of class, I can deal with it. Basically like office hours. And we'll try to have some time on Thursday if there's questions. So anyway, so we're going to start the next 2 weeks are going to be, turn that off, that's too, right. The next 2 weeks are going to be about waves. So when you took 111, we talked a little bit about springs and oscillators, things like pendulums, things that moved back and forth, and basically their motion was periodic. But it was just one single thing moving. Now we're going to extend that. I probably made a comment to my class that essentially everything in the universe is a spring or a set of springs. And we talked about that a little bit. We talked about like deformation, nothing serious about it. But, you know, basically what's going on in real materials is the atomic bonds act a little bit like springs. You can stretch them and increase their energy or decrease their energy. And they kind of look like springs. They don't, you know, they're obviously different causes. But from the point of view of physics, it's a spring. So we're going to start out introducing types of waves, just how to characterize them. And then we're going to talk about the properties of them, what they look like. So, you know, things like frequency, period, wavelength, amplitude. What did those terms mean in particular? And then probably Thursday we'll be talking about the velocity of waves and, in a sense, the energy that's carried by waves. Right? In a sense, when we talk about a wave, we're talking about an oscillation moving. But what we do is we take a thing, we put some energy in one end of it, and it goes through to the other end. It's an impulse of energy that travels through something. So we can talk a little bit about the rate at which that happens and the energy that's carried. And then we can talk about how to deduce that from material properties. So this is getting slightly into like musical instruments. How do you know the frequency of a string on a guitar? You only figure it out from this mass of the string and the length of it and the tension in it. All right, so that's where we're going to go from there. And probably today will just be the introductory stuff. So the thing you do at football games, that is a transverse wave. The idea is that you can see in the, so I kind of put two things up here. You can see in the animation that the actual particles in the wave are not moving horizontally relative to their starting position. They're moving vertically. But the impulse, you can kind of see, is traveling, well, it kind of, this is not enough to determine it. In the other picture, though, the impulse is moving left or right. The medium, the thing that's shaking, shakes perpendicular to the direction the energy travels. So, the example I gave, if you're at, well, not this year, but in the past, if you were in a football stadium and everyone's woo and did the wave, the information where people were standing up and sitting down, the pattern of the wave went around the seats of the stadium. But the people didn't do that. They moved up and down. They got up out of their seats and back down. If you were to do something like shake a rope or a string and send pulses down the length of it, that would be transverse. You might also take a slinky and shake it side to side. And that's what the lab will involve, is we're going to use springs to investigate the properties of waves. That will be next week's lab. Longitudinal waves are like traffic. So here, it's a little harder to see what's going on, but this is more like taking a slinky and sending pulses down the length of it. You bunch up a bunch of particles. In the animation, you can see that the particles bunch up and then the bunch moves. In this case, it looks like it's moving left or right. But the idea is that the particles move in the direction the energy moves. Now, our analogy here is going to be with the slinky in the bottom picture. If you look at any particular coil, it doesn't move that far. It just moves back and forwards a little bit. That's going to be kind of important. It's not that a chunk of the stuff moves. It's that the state of that chunk of stuff changes. It goes from compressed to stretched. Now, probably the example that matters to y'all the most is going to be sound. For longitudinal waves, all right, when we speak, we push air out of our mouths and then it leaves out into the world. Or if we play a sound out of a speaker or out of an instrument, it leaves the opening and the medium is a bunch of gas. And we're going to talk about gases in maybe 3 weeks. But the gist of it is there's nothing really holding gases together. There's not that relationship of springs as atomic bonds, atomic bonds as springs. In this case, the particles are all bouncing around at each other, and it's pressure. It's the pressure of the gas acting essentially as a spring. When particles get closer together, the pressure rises, and so there's an outward force that pushes the particles apart. When the particles spread apart, then it's a lower pressure, and the outside pressure pushes particles back in. So it looks mathematically like a spring, but it's a completely unintuitive analogy. But ultimately, the wave still works. We push a chunk of air out of our mouth when we speak, and that chunk pushes other chunks of air as it gets to you. And so it's a pressure wave that moves towards you. All right, so you can also have combinations, and the biggest example is water waves. If you've been to the ocean, or if you've been to one of those wave machines, which are really fun sometimes, the gist of it is you can see the wave on the surface, and you can see it move, and it looks like a transverse wave. It is above the surface. But if you were actually in that wave, generally your position doesn't change over a wavelength. You don't move with the wave. You kind of move on a circular path. is that because the waves on the surface is picked up and down, but it's also being pushed side to side. There's water to either side pushing the wave. Now, for those of you that might be interested, another example of this is earthquakes. Say there's an earthquake somewhere. Virginia tends to have what minor earthquakes, and they tend to be out on the on the coast, maybe a little bit inland, but we can feel them. But the gist of it is the wave has to come through the ground, and so there's two types of waves. One is the pressure wave that comes basically a longitudinal wave, and it goes everywhere throughout the earth. As it spreads out, it weakens. It's the strongest nearest to the actual earthquake, nearest to fault. But then there's a surface wave, an S wave, that moves along the surface of the ground. And that tends to be the thing that does the damage to a building, in that the ground is both moving side to side and up and down, and it basically shakes the building apart. So that's another type. And because it's limited, it's essentially limited to solid material. So it lets us know what the interior of the Earth looks like. Effectively, the pressure wave can go through everything. The surface wave is limited effectively to the solid material on the surface. And so we know that the interior is not solid. It can't really get through that very well. All right, so we have a transverse wave. The point of this question is to get you to have a visual in your mind of what's going on with the wave. All right, when the energy is going to translate left to right. All right, the wave is traveling to the right, which means we've made a pulse in a slinky, and that's what it looks like right now. In a moment, it will be to the right of that, like that. And so we ask, well, the points that we've marked, A and B, what are they doing? Well, this is a transverse wave. So the points on the slinky, the points in the medium, are moving perpendicular. So the perpendicular direction is up and down. So you can, look at all these choices, A through D. They're all things moving up and down. But to deduce which way the thing's moving at a given instant, we have to look at, in red in the image here, that moment later, what's happened. And so for point A, let me see if I can go over here and try to annotate this slightly. So point A, it kind of looks like it's risen a bit. It's went upwards. Point B looks like it's went downwards a bit. All right, so the impulse has moved to the right. That's going to make point A come more to the top of each of these peaks. And so we want a solution that says A is moving upwards and B is moving downwards. And that happens to be D. All right, so does that make sense to people? All right, when we talk about the wave moving to the right or to the left, what we mean is that the shape of the wave moves. The medium moves in accordance whether it's transverse or longitudinal or surface. All right, so the next slide here, we're going to define properties of the wave. Now I have better slides in a minute for some of this stuff, so I'm just going to point out sort of, let's see. So the amplitude. Amplitude is how far a particular chunk of the wave moves from that equilibrium, from that undisturbed position. And so we can see in these images that, let me see if I can zoom in a bit. There we go. You can see there they're marked with the letter A. It's from the equilibrium to that maximum position. The amplitude is where the energy is stored. Effectively, when we want to talk about the energy of a wave, it has to do with effectively the amplitude squared and then times some constants. And you can think about this. If you were going to shake a slinky side to side, right, your motion, your input of energy is moving your hand side to side. That puts kinetic energy into like the first couple of coils of the slinky, which transmits it onwards to the next few. All right, so if you wanted to put more energy into it, you would shake it harder. You would move it with a wider amplitude. So the wavelength and the period. The wavelength is the distance that represents one cycle of the wave. So if you remember back to your trig classes, right, from physics 1, we talked about sines and cosines, and they were triangle bits. But from your trig classes, they're also functions. And when you plot them, you get these sinusoidal curves. So in the trig class, the period would be the bit of it that is the repeating bit, from 1 0 to another 0 with the same slope. So for the wavelength, we're going to take a plot of the distance. Basically, we're going to look at the entire medium, and we're going to see the pattern. And you could make one of these plots for longitudinal waves. So like for sound, you make a plot where the y-axis is the change in pressure in the air, and the x-axis would be distance through the air in the room. And that would give you something that looks very similar to the, it would be a sinusoidal graph. So what we've got here, we've indicated, the wavelength is once, and what's happening is in a wave, the wavelength is the time it takes for it to return back to the same point with the same velocity. Right, if you think about in springs and pendulums, one period of the oscillator, the spring or the pendulum, whatever it was, one period was the time it took for it to return to the same spot with the same velocity. And there's a reason for that is, no, that was not what I wanted. I wanted to zoom in. So on here, this distance here is it returns to the same spot, but it has different velocity, right? And the beginning case, it's going upwards, and in the end case, it's going downwards. So that's half of a wavelength or half of a period. Now, if you measure from peak to peak or trough to trough, you don't end up with that problem, but you can measure from any arbitrary point on the wave. So you have to have this extended definition. So what we're doing, what I'm saying is I'm defining the cycle of a wave is same position with the same velocity. So the period uses the same definition, but the plot is to look at the position versus time. So we look at one particular coil in the spring and we ask what it's doing over time, and we plot its position. And in the frequency, is representing a counting. We're saying the frequency is the inverse of the period. Right? So when we state the period, we would say, well, this pulse of the wave crossed a meter in 5 seconds. So its period is 5 seconds. Or really what we would want to say is this pulse, its wavelength is 5 meters long, or 1 meter long, however long it is. But it crossed in front of us, and it took 5 seconds to do so. So its period is 5 seconds. The frequency is more of, we're going to set and count for a period of time, say a second, and ask how many pulses go by. And so if it takes 5 seconds to go by, we only see the first fifth of it, the first 2/10 of a second. So it's 0.2 parts of the wave per second. All right, so the frequency is a counting. We're counting the number of waves that go by. Now, I want to be careful here is when we talk about other things with waves, some of this stuff will vary because it depends on the medium. All right, the amplitude is independent of everything else. The wavelength and the frequency are related. They're related to the speed of the wave. And the speed is related to the material properties. And so what happens is the thing that doesn't change is the frequency. The frequency should stay the same. If something like, say, I'm yelling in this room, and then the sound goes into a body of water outside the room, say into the pipes, well, it's going to go faster in the water. And so the thing that changes is not the frequency, it's the wavelength. Anyway, I'm getting ahead of myself. I'm sorry about that. The important things I want you to take out of this and right now is the amplitude and the wavelength. So this is another one. All right, so some of these questions are written for, probably the bottom of the high school class. So these should not be too bad, but the gist of it is, can you identify a wavelength on this wave that we've marked where there's 6 points marked? So we can go through and look at, we realize that if we pick a point, we got to pick another point that looks like it. So, for example, let's pick point B. All right. Point D doesn't look like point B. It's going in the other direction. It has a different velocity. That would be half a wavelength. The corresponding point to B would be F. That would be a wavelength. Now, that's not an answer, but that does represent one wavelength. Now, there is another one, and it's one of the choices. When we look at it, it's A and E is also a wavelength. And so we can look at some others. A to C is essentially like B to D. It's half a wavelength. And then A to F is more than a wavelength. It's like a wavelength and a quarter. But essentially, the answer for this is A to E. Does that make sense to people? So this question's about an amplitude. We're going to have a wave, a longitudinal wave in this case, though that's not a huge deal. And the amplitude, all right, the point is to talk about the amplitude, because what's happening in the problem is we're asking what a particular coil is doing during a bit of the wave. That is, we send a pulse down this slinky. It moves 2 meters per second. And what we want to know is how far a part of the slinky moves during a period of the wave. All right, an idea is that we want to examine some of these answers here as well. All right, and if we look at A, each particle in the slinky moves 2 meters each second. What that looks like is, this is my slinky analog. It looks like that. It just move, you know, you take the whole thing and you move it. It doesn't look like a wave. The other ones look like amplitude. So what's going on? We have, here's our slinky. Close enough. Pen. What I want is to change the color. It's weird. Anyway, so we'll pick this point here. So following that point, it's longitudinal, which means the wave moves along the medium, so it moves that way. And automatically we can see, well, the only one that's longitudinal is C. But it's going to move that way during the first quarter of the period, and then it moves that way, and then it moves that way again, and then it moves back. So it moves over a period of the wave. A part of the medium moves 4 times the amplitude. And that's the thing that when we ask that in some contexts, it kind of trips people up, is if we have a wave that looks like, you know, a transverse wave and it's moving up and down, people get the image in their head. Well, that point doesn't really shift along with the energy. It doesn't do anything, you know, it just kind of sits there. But no, it actually is moving, and it moves some distance. And the gist is that the distance is 4 times the amplitude per period. So the answer for this one is going to be C. All right, I've included this slide so that you just have a refresher. Hopefully everyone's taking notes so you know what amplitude, wavelength, period, frequency is. So we have essentially what we have is a function that, or that is that what we've described as a sine wave or a cosine wave in your trig classes, the cosine or sine function. All right, we've described that. And if we have a wave that has all these properties, there should be some function that describes the shape of the wave. Idea is that we can find the amplitude based on time and position, or we can find a particular position of a particular point on the wave. And so we have a plot of it at least. Right, so our plot, all right, we have y and x. So at this moment, it's going to be a plot of horizontal and vertical position. So this is looking like a snapshot. You take a camera and you take a picture of the wave as it moves. By the way, while it's on my head, make sure you bring your phone to lab on the next 2 labs. The idea is that for some of this stuff, we're going to be like actually shaking springs. And it was worthwhile to video it so you can go back and review the footage. So, plus if you have slow motion on your phone, that's also useful. You can slow things down frame by frame and look at it. So the idea is that we're taking a snapshot of all the particles in a wave in the medium, and it looks like this. And so we can identify certain chunks of it. But the idea is that that is a function that has some equation for it. Here's the equation for it. Now the point of these next few slides is to go through and identify what all these terms are. But it's clearly, in this case, trig function, a cosine function. The amplitude A is right out in front. And then everything inside the cosine function is some, well, for trig functions, you got to put some angle into it. So there's a way of defining the angle for this, which effectively tells you where you are along oscillation. So K here and the weird W is omega. Those things are related to the wavelength and the frequency. And then the phi at the end, that's the phase. The phase is mostly unimportant for what we're going to do, but I want to, if you have a question about it, here's what it is. If we put in 0 for everything else, then we would have A cosine phi is something. And that's got to describe this one point on the y-axis. Because, we put in x is 0 and t is 0. So phi here indicates this point. It sets the value of that point, in a sense. Now, so what that means is if you have say you have a calm pond, right? So a way you could make a wave out of it is to drop a rock into it. And the water would start at equilibrium, and then it would move around, and you would have your surface wave on it. Another way you could do it is to lift a bucket of water out of the pond. And so your water level starts low instead of at equilibrium, and water rushes in to fill that gap, and you get a wave out of it. Probably a better analogy is to go back to oscillators. So in the labs where you measured the period of a pendulum, what everyone did was they pulled it back to a beginning point and then let it go. What you could have done is set the velocity instead of setting the starting position. You could have kicked the pendulum or swatted at it, made it move with some velocity, and started at an arbitrary. The idea is that you can start this oscillator with arbitrary conditions, arbitrary velocity and position. And so that's where you set it. So otherwise, don't worry too much about that. So these plots that we're going to show are looking at a wave that depends on both the position and the time. But what we're going to say is we're going to look at one instant and take a snapshot of the whole wave, or look at one point and look at how the wave evolves over time, because that's easier for us to do than to try to follow all the ripples on a pond. So if we just look at one point and see the oscillation over time, this is what happens. We basically get rid of the X part of this. And so we have something that looks like an oscillation, like a pendulum oscillating. And you get a function that looks like this. And so this thing in here, omega, we've used that before in class. That was the angular velocity in rotation. That was the angular frequency in springs, if that came up. And it's related similarly to the frequency. Yeah. So the period here we mark on the graph. The period is, the distance between equivalent points in the wave. Right, and we're being very clear, this is amplitude versus time. This angular frequency is just 2 pi divided by the period. And since you know that the frequency is 1 divided by the period, you know that omega here is 2 pi f. All right, so you've hopefully seen that before when we talked about one thing oscillating. And you've also seen it when we talked about rotation. And there's an analogy between a wheel rotating and a spring oscillating. So if instead we just take a picture of the wave, so in one instant, then the space we're going to have between crests of the wave is going to be a wavelength. So this is a picture of the wave. This is amplitude versus position. And so it captures the entire wave, but only at one moment. So we have a wavelength that's defined. And then we have a function. Well, last time we got rid of x, this time we're getting rid of t. And so we have a is cosine kx plus phi. Now, if you remember your trig, you remember that you can't put units inside of cosine and sine and other things. Basically, whatever you put in a function like that has to be unitless. And that should have come up in physics 1 at some point, is, you know, even in finding the sides and angles of a triangle, if you use a trig function, you have to put two sides in, because otherwise you put a unit in and it doesn't cancel out. So x here is the position, it's in meters. K here has to be something per meter. It's a counting function in a sense. We're counting the number of cycles of the wave that fit in a certain distance. That's what's called the wave number. And so that's what we define. And it's effectively 2 pi divided by the wavelength. Okay. So that's where these terms, now, from your perspective, you're going to use the wavelength, lambda, and the frequency, f, much more than anything else. But these equations, you know, they are there for you, that you need to know them. All right, so I'm going to go on for a little bit. We're at the point where we want to talk about speed in waves, and I think it's worthwhile to keep going for a bit. So if you guys were a upper level physics class, I would say that, well, we have the position. We would want to find the velocity, and that's taking a derivative. From your perspective, we want to find the change in y, the change in this function over time, delta y, delta t. You can do that. The idea would be to go through, and maybe you saw this in oscillators, an argument, you know, making the analogy with rotation, that, you know, the oscillator looks like something rotating, and you're just looking at one dimension of it. And so if you have a cosine function here, then the change in it would look like a sine function. But the idea is that you could come up with a velocity out of these equations. And so if you go and do that, and I don't go through the details of it, the gist of it is exactly what you would expect intuitively, is if I see a wave moving through a medium, then I can just follow one peak of it. And I know how big it is. I know how big a wavelength is because I can see the whole wave. So I would follow, say, this peak there. So on this picture, let's mark this one. We'll follow that one, and we'll ask, well, what happens when it gets there? So delta x over delta t is lambda o. Ooh, that went bad. Lambda over t. That's going to be our velocity, and that's what we end up seeing. And so if you go through the mathematical way, you end up with the intuitive picture that the speed of a wave looks like the distance a point in the medium a distance the energy travels in the medium, which in one period is one wavelength. So it's lambda over t. And since the frequency and period are related, we can write it as F lambda. So I've got another, I put the image in here so you can see, all right? The idea is that, so your hand is acting as a single oscillator that's driving the wave in this little picture, and your hand makes one period of motion, and you generate one wavelength. And that's where you get V is lambda over T. So the most important thing that you'll probably use is something like this, is either F lambda or lambda over T for the velocity. All right, and then students always kind of churn up and get this kind of wrong. They do lambda times T or F divided by lambda or something. And the point of it is to look at the units. So the units for frequency is 1 over second, which is given a name Hertz. So our frequency is 1 over seconds. Our wavelength is in meters. So our velocity should be in meters per second. That's kind of, you know, if you're trying to recreate the formula for some reason, that's what you're trying to do. You're trying to look at the units. So, yeah, I wrote stuff here on top of this. This one is not nearly as important. This is the big one. But the relationships between lambda and K, between wavelength and wave number, or between frequency and angular frequency are, you know, they're useful. And so we can define the velocity in terms of angular frequency and wave number. So you do also get that, but generally, this is the equation. That's the one you want. So let's do an example here. So this is going to talk about light, and light's odd. We'll talk about it at the end of the year. It'll be the last thing that we talk about, but it is a wave. Something is waving, right? There is a medium, and it was kind of hard to understand up until about 150, 200 years ago that the stuff you're going to study in about 6 weeks, electricity and magnetism, when we talk about, say, you know, the electric field or the magnetic field of an object, that thing can change over time, and it can act like the medium and carry energy. It can wave. So light is going to be a wave consisting of electric and magnetic fields. So we're going to specify that the speed of the wave is 3 times 10 to the 8 meters per second. The bit that we would end up skipping this semester is that is always true, and it's a constant. It's actually more precise than that, but that's okay. Now, if you're listening to the radio, who listens to the radio anymore? Like I did, because I got tired of ads on Spotify. If you listen to the radio, or you tune a knob, what you're tuning in, the number on it, is the frequency. So, you know, we have 2 of them. AM is very low frequency in a sense, only about 1,000 per second. Sorry, about 1,000,000 per second, sorry. Low for waves, or low for light waves. And an FM wave is about 10 to the 8 oscillations per second. Right? And so what we want to do is figure out the the wavelength of these waves. Now, while you're thinking about that for a minute, you know, you're thinking about the thing I just told you, V is F lambda, and then doing some math on this. Here's your intuition as to whether your answer is right or not. If you have an FM radio, it has an antenna out the back, and your antenna on your car, let's say, is only about 17 inches long or shorter. It's not exactly a big antenna. Your antenna size matches roughly your wavelength. It basically picks up a copy of the wave and then a copy of the next wave, and so on and so forth. It's not exactly that. But if you're listening to an FM radio, you expect it to be on the order of a couple of meters. All right, it's not going to be 1 meter, not 10 meters. If you have an AM radio, you might be like, well, where's the antenna on this? It's not the thing that, you know, like you have an AM FM radio. The FM bit is just a stick, just a piece of metal. The AM bit's actually a coil that's inside, and it's a very long coil. A better visual is looking at the antennas that the transmitters have. All right, the FM ones have just a little thing stuck at the top of a tower. They're on the tower so that they can see farther. The AM ones, the entire tower is the antenna. You're looking for something on the order of, say, hundreds of meters. Anyway, the gist of this is we have the speed, we're looking for the wavelength given the frequency. So we have calculations. Effectively, we move it around, we take and divide both sides by F. So we get lambda as V over F. We plug in. So we have meters per second on top, and then we have per second on the bottom. All right, these hertz are really 1 over second. And so we're left with meters. So for AM, we get a number 244 meters, and that's within our intuition, is we need something big to pick up an AM signal. FM, we get something on the order of 3 meters, 3.26, and that's reasonable. We need something smaller. That makes some sense. It would make more sense if people use radios more, but that's okay. And for some reason, I left a calculation in on the next slide. Yeah, I left a calculation on the next slide. All right, so let's do another one here. Did y'all have any questions about the last one? All right. So this problem is about waves in water. We're going to treat them as roughly transverse waves. They are surface waves, but they still have amplitude. They still have period and wavelength. And so for visualization, when I draw it, it's going to look transverse. So Jimmy and Jenny are on a river. I really need to change those names so they're different or sound different. So they're 5 meters apart. So let's put in 2 points that are 5 meters apart. And there is an oscillation because the boat goes by. And Jenny will be at the high point and Jimmy will be at the low point. So our wave looks like that. And it's going to keep going from there. And we have a stipulation that they're at most a wavelength apart. So that drawing kind of makes some sense. We're not going to put something in that looks like that. That's no good. I'm going to get rid of that. So the drawing we have here, that looks like about about half a wavelength, right? Is if this is 5 meters, the next point, we're going from the very high point to a very low point. Let me not do eraser. Yeah. All right, so the wavelength here would be something like this, and that's 10 meters. Have I done this right? All right, yeah, I've done this right, okay. So the gist of it is we have a wavelength, we have a frequency. V is F lambda, which is 0.25 hertz is 1/2 times 10 meters, and that is 2.5 meters a second. And that's our answer. Does that make sense to people? That's the intuition is sometimes we see something, we see a description of it, and it's hard to deduce, right? So you always draw a picture of the thing and try to deduce what is the thing according to our definitions. What's the wavelength? What's the frequency? Sort of stuff. All right, so that's where I want to stop for today. I'm going to introduce briefly here in the next slide. We're going to look at, on Thursday, how to deduce the speed of waves that are going through a medium. So Thursday's class, we'll finish this out about speed. We'll maybe do some more practice problems of that. And then we'll do the stuff that you need for the lab. Is the reason I go to this slide, we want to send waves in a medium, a spring or a string or something. What happens when they get to a point that's fixed? All right, so for the lab on Monday, we'll talk about reflections and different types of interference. All right, so we're going to get into stuff for next week, but that's, going to prepare for that on Thursday. All right, so do you all have any homework questions? If you don't, you can go. Otherwise, I'll help you with stuff that you have questions on.
Can you explain that big trig equation a little bit more?
What
are the parts of that and what is that trying to help us find?
Okay. Let's go all the way back, Wasn't that part. Here it is. All right, so. All right, so.
I'll come up there.
Yeah, so the gist of this is that. No, that was not what I wanted. Go away. All right, so the parts of it, A, here's your amplitude. All right.
I thought that was what we were trying to find was the amplitude, which is because if the amplitude is y.
All right, so all right, so when we say y, all right, the idea is that we're picking a point on here, say this point, and we're saying, well, it has a value x, and then it has a value, I've drawn that poorly, it has a value y, which might be less than a.
Gotcha.
All right, so the idea is
but
that
it can't ever be greater than a.
It can't ever be greater than a. All right, a represents the energy that's in the thing. So when it's here, all the energy is kinetic energy. It's going up, it's moving. When it's at these points, it's turning around. So it's velocity zero. Those are all potential energies. But so the amplitude represents like the maximum potential energy of the thing.
That makes sense.
Right.
So then is either the time or the position, does one of them have to be zero? Because on one graph, the x-axis was the position, on the other one, the x-axis was time.
Yeah, in general, what happens is when we make a graph and it is, say this is a graph position, then what we're saying is we're picking a particular time.
Gotcha.
The time doesn't have to be 0, but what happens in this formula is we just put in a number. And so we end up with omega t plus phi. We just combine that into one new symbol. It's a different phi.
So one of them will always be 0 then, either x
Effectively,
or t.
yeah.
Okay.
So yeah, so it may actually be non-zero, but in the case of the plot, you don't care. You're just going to pretend that it's 0.
Gotcha.
All right. So in this case, what we're doing is saying phi here represents what happens when t is 0. It sets this point here, but then afterwards, we're just going to look.
So phi is like whatever the same measurement that a is. It's just measuring how far it is from the x-axis to the point.
Effectively, what it's doing. Let's draw a sine wave here. All right. So phi is a measure of basically where you are along that wave. This is 0. This is pi, and this is 2 pi.
Gotcha.
So phi just says, well, if we pick pi over 2 for that, then we have to be there.
Gotcha. Okay.
But you might pick pi over 6 and you'd be closer to 0. All right. So it's just a way of saying this initial point, right? The 0 for this wave actually occurs a little bit before t equals 0 or x equals 0.
That makes sense. Okay.
And then, so, I mean, you're doing the same sort of stuff with either version. Is when you have a plot, right? The typical sort of, let me draw it out here. The typical sort of thing everyone does with a graph, right? So this is going to be sine, is they start it as 0, right? Because sine of 0 is 0. So they start there and they do this. And then when they do cosine, well,
Which is what the equation is.
now they do cosine of 0 is 1.
Yeah.
So they do, and they started at 1. But you could start it at any arbitrary point. You could pick this point, and so you would have to do that. And then
Gotcha.
your wavelength would be from there to.
So
that.
what would phi be in that? So phi would be 0 here, right?
Yeah, phi would be 0 here, and it would be
1?
0. No, it would be 0 here because it's cosine.
Gotcha.
That's weird. This is effectively sine of pi over 2. So you would have cosine of theta is sine of theta plus, well, and then this is 90 degrees is pi over 2. All right, so this is identity, right? You can go from cosine to sine by adding 90 degrees to it.
Gotcha. So what would phi be in like this example? Like if this is like at pi thirds or something.
Yeah.
Then
So
wouldn't phi be?
Yeah, it'd be
It'd be pi thirds.
Yeah, pi over 3 or.
Gotcha.
It might be actually minus pi over 3. Don't worry about the minus sign. The idea is that it's shifted. You can have it shifted the other way. And so it would look like that instead, where the wave keeps going like that. So
Gotcha.
one of these represents the wave being pushed forwards and one pulled back a bit.
Okay, that makes sense.
And ultimately there, because it's a periodic thing, it can have a lot of repeating values. It can be pi over 3. It can also be 7 pi over 3, because that's plus 2 pi.
Yeah, that makes sense.
So,
okay.
Yeah, don't worry a huge amount about, like, the idea is that the wave equation exists and you can get information from it. Like, right, the idea is that your y is a cosine kx minus omega t plus phi.
And since phi is measured in pi, is that why we need the k and the w to have
Yeah,
some
to make
pi's in
these,
there?
yeah, they're just unit fixings.
Gotcha.
And the idea is that you can also write this as a cosine 2 pi, 2 pi over lambda x minus 2 pi ft plus phi. And then, that makes more sense. It's wavelength, but it's made correctly, and in frequency, and it's made correctly, right? Because those f and t is unitless. And then just have this 2 pi and it comes out. So, so the idea is that a cycle of the wave is 2 pi, and then this tells you where you are in that cycle.
Gotcha. Wouldn't that come out with units of per meter? Because
You would have
because the lambdas in
X
meters.
is in meters and lambdas in meters.
Okay, that makes sense.
And then you would have, here, you'd have
phi is already
seconds times 1/seconds.
Gotcha. Yeah, I just didn't.
Yeah.
My brain didn't make the
Yeah.
connection with the X would cancel the lambda.
Okay.
Okay, well that makes sense.
Yeah.
Thank you for
No
helping.
problem.
I appreciate it.
Again, it's, don't worry too much. It's more worry about, V is F lambda and the definitions of frequency and wavelength, and can you pick them off a graph?
Gotcha. Okay. Yeah, if I need to use that equation, so long as I can figure it out, I think I'll be all right. Well, thank you for your help, and
You're welcome.
you have a great day.
You too.